reality, information, universe. Forget everything you think is solid. Forget the chair you're sitting on, the screen you're looking at, the very air you're breathing. For millennia, we've built our understanding of the universe on a simple, intuitive foundation that the world is made of. We call it matter and energy. It's tangible, it's physical, it's real. But what if that's just the surface? What if, when you peel back every layer of reality, past the atoms, past the quarks, past the vibrating strings of energy, you don't find more stuff at the bottom? What if all you find is a question, a choice, a single binary piece of information? This is the precipice of one of the most profound and reality-shattering ideas in all of science. The concept that the universe is not made of physical substance, but is fundamentally composed of information. That existence itself isn't a collection of things, but a computation. That reality is a code. This isn't just philosophical musing. It's a concept that grew from the deepest, strangest roots of modern physics, and it was given its most famous name by the legendary physicist John Archibald Wheeler. He was a titan, a collaborator of Einstein and Bohr, who coined terms like black hole and wormhole. And he distilled this revolutionary idea into three elegant, cryptic words: it from bit. It's a phrase that deserves to be unpacked, because within it lies a complete inversion of our view of the cosmos. The it represents every physical thing: an electron, a planet, a galaxy, the fabric of space-time itself. It's the stuff of reality. The bit is the fundamental unit of information, a yes or no answer, a 0 or a 1. Wheeler's proposition was that every piece of the physical world, derives its very existence from the bits, from the answers to binary questions posed at the quantum level. To grasp this, we have to journey into the bizarre world of quantum mechanics. In the classical world of Newton, a ball is either here or it's there. Its properties are fixed and definite. But in the quantum realm, a particle like an electron can exist in a superposition of states. It can be spinning both up and down at the same time. It can be in multiple locations at once. It's not a definite it yet. It's a cloud of probabilities, a wave of potential. So how does it become a concrete it? Through observation. The moment we measure the electron, the moment we ask the universe, is it spin up or down? Its cloud of possibilities collapses into a single, definite answer. The universe provides a bit of information: yes or no, up or down, here or there. And in that instant, the it, the particle with a definite property, springs into being. This isn't just a side effect. Wheeler argued this is the it of reality. The universe, at its base, is a seething ocean of quantum uncertainty. Reality as we know it is continuously being formed, bit by bit, through these acts of observation, these resolved questions. The physical world, in this view, is not a pre-existing stage on which events unfold. Instead, it is a participatory reality, constantly being painted into existence. The observer isn't a passive spectator watching the cosmic movie. The observer is fundamentally involved in writing the script, one binary choice at a time. This completely flips the script on causality. We usually think that first there is a physical world, and then we can gather information at it. It from bit suggests the opposite. First, there is information, and from that information, the physical world is constructed. The universe doesn't just provide information, the universe is information. Think of it like a video game. When you're playing an epic open-world adventure, the entire vast landscape doesn't exist in your computer's memory all at once. That would be impossibly inefficient. Instead, the game engine only renders the parts of the world that your character is currently looking at. The tree on the distant mountain only pops into existence as a detailed object when the game's code determines it needs to be observed. Before that, it was just a set of abstract data, a probability. Our universe could be operating on a similar principle of cosmic efficiency. Physical properties are only rendered into existence when a measurement or interaction demands it. The rest of the time, they exist as pure informational potential. This radical idea forces us to reconsider what we mean by real. Our senses scream at us that a rock is a solid, unchangeable thing. But physics has already told us that this rock is mostly empty space, a frantic dance of subatomic particles governed by fields of force. The it from bit hypothesis takes this one step further. It says that the rules governing that dance, the very existence of those particles and forces, are algorithmic. The laws of physics in this view are not descriptions of a pre-existing mechanical world. They are the algorithm that processes the information, that takes the bits and computes the its. Every law, from gravity to electromagnetism, could be a line in the universe's source code. This is a universe where every physical interaction is a form of computation. When two particles collide, they are exchanging information, updating their states according to the cosmic program. The entire unfolding of the cosmos, from the Big Bang to this very moment, can be seen as one colossal ongoing computation. But if this is true, if reality is just the output of a vast information processing system, then this isn't just a philosophical game anymore. It becomes a testable scientific hypothesis. And if it's true, there should be clues. There should be evidence embedded in the fabric of the cosmos, hints that point towards a digital, computational core. And that's where things get truly mind-bending.
Digital cosmos proof. So the universe might not be a grand clockwork machine, but rather a grand cosmic computer, with reality itself being the output. John Wheeler's it from bit is a beautiful, provocative idea. But is it science or is it science fiction? If our cosmos is fundamentally built on information, if it's a computation or a projection, then the evidence shouldn't be hidden in some esoteric philosophy. It should be right there in our most advanced physics, screaming out from the most extreme corners of the universe. And it is. The clues are mind-boggling, and they come from the deepest mysteries physicists are grappling with today, starting with the darkest, most enigmatic objects in the cosmos, black holes. Our first major clue comes from a paradox that almost broke physics. According to Stephen Hawking, black holes evaporate over immense timescales, emitting what we now call Hawking radiation. But this radiation is thermal, meaning it's random and contains no information. This created a nightmare problem. If you throw a book into a black hole, the intricate information that makes it a book is seemingly scrambled and then utterly erased from the universe when the black hole evaporates. This violates a core tenet of quantum mechanics, which states that information can never be truly destroyed. It's called the black hole information paradox. The struggle to solve this led to a breakthrough by physicists Jacob Bekenstein and Gerard Tufte. They discovered something absolutely bizarre. The amount of information a black hole can contain, its entropy, is not proportional to its three-dimensional volume, as you'd expect. Instead, it's proportional to the two-dimensional surface area of its event horizon. Think about what that means. It's as if you tried to store a library of books, but the number of books you could fit depended not on the size of the room, but on the square footage of its walls. This was a revolutionary clue. It suggested that all the information for a 3D object, the black hole, is somehow encoded on its 2D boundary. This idea was then supercharged by Leonard Susskind into what we now call the holographic principle. It proposes that this isn't just a weird quirk of black holes, but a fundamental property of the entire universe. The principle suggests that our three-dimensional reality, everything we see and experience, might be nothing more than a holographic projection of information stored on a distant two-dimensional surface at the edge of the cosmos. We might be the hologram, not the film it's projected from. This is not an analogy. It's a mathematically rigorous concept that provides a powerful piece of evidence that information is the primary reality, and the 3D space we inhabit is secondary, an emergent property of that underlying code. Our second clue comes from what Einstein called spooky action at a distance, quantum entanglement. When two particles become entangled, their fates are linked in a way that defies our classical intuition. No matter how far apart you separate them, across a room or across a galaxy, if you measure a property of one particle, you instantly know the corresponding property of the other. It's as if they are communicating faster than the speed of light, which should be impossible. But from an informational perspective, it makes perfect sense. The spooky connection isn't a physical signal traveling through space. Instead, the information about the two-particle system exists non-locally. The bits that define their linked state aren't located here or there. They exist outside of our conventional 3D space. This suggests that reality is built not just on objects, but on correlations and relationships, on pure information. The universe cares less about where things and more about how they are informationally connected. The third clue is hidden in the very texture of space-time. For centuries, we assumed space and time were smooth and continuous, like a perfect sheet of paper you could zoom into forever. But many theories in quantum gravity suggest this is wrong. They predict that if you could zoom in to an unbelievably tiny scale, the Planck length, about 1/trillionth of the size of a proton, you would find that space-time is not continuous. You would find fundamental, indivisible units of space-time. Space-time is pixelated. If this is true, it's perhaps the most compelling evidence of all. A smooth analog reality can be infinitely complex, but a reality with a finite resolution, a smallest possible pixel, behaves exactly like a digital system. It behaves like a simulation. These clues, the holographic nature of the cosmos, the non-local information of entanglement, and the potential pixelation of space-time, all converge on one staggering conclusion. The universe we perceive is an emergent reality, a user interface generated by a deeper informational code. This leads to the ultimate questions. If the universe is a computation, what is the computer? If we are living in a hologram, who is the projector? And what is the role of consciousness, the one thing in the universe we know of that processes information to create an experience? Is consciousness merely a product of the cosmic code? Or does our act of observation, of becoming aware, play a crucial role in rendering the information into existence? We don't have the answers yet, but the clues are all around us, in the mathematics of black holes and the dance of quantum particles. The physical world may just be a shadow, and the true reality is written in a language we are only just beginning to learn. The code is all around us. The question is, are we ready to read it?